So for the cadence, we were having 25 to 50 licenses. But for this TCAT, since it's a very expensive tool, so we are having only 5 licenses for it. So we have to manage like that, so that each and every student can able to access the tool also and submit the assignment in the due course of time, whatever the time allotted to you. For that purpose, I'll try to make groups of 3 students. You will not be able to unmute your mic. After every 10 to 15 minutes, I'll give you some time. If you have any questions, you can ask. And if I'll try to unmute you from my side from in that duration of time. If you have any questions, you can ask. Meanwhile, if you have any doubt, you can type the message. I'll read your message and try to answer your question. So uh, basically we are having only 5 licenses, so for that reason I will try to make the group of 3 students. By 3 or 4, I'll see the number of counts, how many students have registered for the course. According to that, I'll make the group, and in groups you can perform the experiment. So basically, as I told you, we will use a TCAT software for this. So there are many vendors which provide the TCAT softwares. So here we are using the Centerus TCAT tool, which Synopsys Centerus TCAT tool, which is the vendor is Synopsys. So I'll just share my screen and I'll give a brief introduction what a TCAT tool is and how we will use that tool and how we will go further in this lab. I'll just share my screen. So basically, whatever the TCAT tool, technology computer design tool we were using, this we will use to whatever the semiconductor device, because this is a subject related to the device, MOS device, whatever the devices are there. So we will use this TCAT tool to design our device and see the simulation, how a device works. So basically, if we talk about the device, semiconductor device, so there are single terminal devices, there will be two terminal devices, there will be 3 terminal devices. So in each of the experiments or lab, we will try to design a device and we will see the simulation of that device. So this, for that purpose, we will use this TCAT tool. So why we are using TCAT tool? So to see the fabrication process, how we can't, since to fabricate any device, it is very expensive and we need to set up the fab lab for that, for the fabrication of any device. So for just simulating how a fabrication takes place for designing any semiconductor device, how the fabrication steps, what are the fabrication steps we follow, we try to emulate that steps using the TCAT tool. One thing. And second thing, we will see the properties or characteristics of a device. For example, if we talk about any device, PN diode, how a current of a PN diode behaves when a voltage across it is applied. So this behavior we can see using this TCAT tool. So as I told you, it reduces the fabrication cost and time. We need lots of money and time to fabricate any device. So before that, before final fabrication of device, we can just see this, emulate that same fabrication process using this tool. So it is widely used in VLSI and semiconductor industries. So as I told you, there are mainly 3 types of process TCAT. Process TCAT tool means we are following the process, whatever the process are there to fabricate a device: oxidation, diffusion, oxide layer deposition, CVD deposition. These are the various processes which are used for fabricating any device. So in process TCAT, the process we follow that process to fabricate a device. Second is device TCAT. In this, we construct a device. We just make a device by using the coordinates, whatever the length and size and width of our device. If we know that, using that coordinates, we will design our device. Once we will design our device, we can see the properties of that device. This is circuit. That means if you know how to design a device, using that device, you can make different circuits also. So for one experiment out of 5 experiments, we will see the process ticket also. And for the rest of the experiment, we will see the device, how we can make a different 2D device, 3D device, that is normal MOSFET, FinFET, double gate MOSFET using that ticket. So as I told you, this process ticket follows the various process that is oxidation, diffusion, implantation, etching. These are the fabrication steps. You will be taught in detail about this in your class. Whenever there will be theoretical class, you'll all get to know details about this various process of fabrications. Device ticket, I told you, once we construct the device, we can see the IV characteristics, how current varies when voltage is applied across the device, what is the threshold voltage, what is the leakage current of the device. These are the various vendors. As I told you, there are various vendors which provide the ticket software. So there are Synopsys ticket, Centera, Silvaco, Cosmol, Ogenda. There are various companies which provide this ticket software. Out of this, we will be using Synopsys Center's ticket. So slides I'll share in the notes. These slides are not that much. This is just a brief introduction about the tool. So whatever you will need to how you will use the tool, that proper demonstration in slides and proper videos will be provided to you. So this is how we will go, how ticket software works. First, we create the structure. Whatever the device you are, that detailed how we will do, I'll again explain while I demonstrate in the tool. This is just a simulation flow, how a ticket software works. First of all, whatever the structure of a device. So device means MOSFET. MOSFET is a device, 3-terminal device. Then diode, which is a 2-terminal device. FinFET, which is a 3D structure device. So these are device. So the structure of device, whatever the structure, that means size is what is the size of different regions of the device, that comes in the structure creation. We will be given all the dimensions of our different regions of the device, according to which we will create the structure of our device. Then mesh generation. Mesh generation means that, again, I will tell you in the detail, breaking the device into small blocks so that proper physical model should be applied to that device. That is more physical model selection. So there are many models, numerical methods models, which are used to simulate the device. So out of this, we have to select any particular model to run, that will be run across our device. Then simulation execution. Whatever the simulation you want to execute, you will execute that simulation on your device. Once you have constructed the device, now you want to simulate that device. So that is simulation execution. And finally, once the device is simulated, you will analyze the result. Whatever the results you have got, you will analyze that result. Last, what are the application of this ticket tool? So you will use it to design CMOS, FinFET, solar cells, MEMS devices, memory devices. All these are designed using the ticket software. This is what are the advantages of this ticket tool. So faster design optimization. So before fabrication, if you just, I am giving you a game example. If you want to design something, so before designing that things, you can, in this ticket tool, you can emulate that process. So if you want to optimize that device, for example, if you want to increase the current, so for increasing the current, you have to make, for example, for your current scenario of your device, you are getting 2 milliamperes of current. For a current scenario of your device, you are getting a 2 milliampere of current. Now you want to increase that current to 4 milliamperes. So once you have fabricated the device, now if you want to increase the current, you have to again fabricate that device. So the previous device which you have fabricated, that will be not of your use. That is not of your use. So for improvement in the current, you again need to follow all the fabrication steps. But with the help of TCAD tool, what you can do, you can just, whatever the device you have designed in the TCAD software, you can optimize different values. You can increase the doping concentration, you can increase anything and see the effect on current. And by doing all these alterations and variation, you can see in which combination you are getting the maximum current. So this optimization process can be done faster using that TCAD tool. As I told you, for fabrication, you don't need to do various iteration before fabricating the device. You can do the various iteration in the TCAD tool itself. You can predict the device performance. That means for particular condition, what is the performance of device, you can predict your this tool. And again, you can scale your device to nanometer. For example, if you want to make a 10 nanometer device, 8 nanometer device, and analyze that device, you can use this software to do that. So this is the basic why we are using the TCAD tool and how we can, for why we are using the TCAD tool. So any doubt in this? These are the basics of a TCAD tool. Now, how we will go through the experiments. For that, I'll just show you how we will go through the, for example, first experiment, how we will go through it. I'll just demonstrate that. So this is the whole this block diagram. So shows you how we will go through the experiments. What we will do in that whole, each and every experiments we have to follow. What are the process we have to follow through this flowchart? I'll explain you. So as I told you in the PPT also, you will first of all you have to make the device. Whatever the device constraint, you will be giving a problem statement like design a MOSFET, yeah, design a PN diode with the length this, length of device is this, breadth of device is this, doping of P region is this, doping of N region is this, channel length is this. All the specification you will be given. According to that specification, you have to design a device. So first and foremost thing is you have to design a device. So for designing any device, there are two ways to design that device. For designing any device, there are two ways to design that device. Either in the GUI mode, that is like a color paint window will be there. You can make a device. You can make a device with the specification by you scrolling your mouse. You can make a device. So first way is you can make a device. Whatever the specification of a device you are provided with that proper specification, you can make a device. The second way is you can script it. You can write a script for that. For whatever the specifications are given, you can just write that specification in the form of a script, which can generate that device. So these are the two ways in which you can construct a device. So if you make a device, if you are making a device, these are very important steps. You should just see that. Then in the due course of experiments, you will get clearly thoughts how the lab is going on, because this is all scripting tool. You have to just write the commands and run the simulations. So please concentrate on each and every statement so that it will be beneficial for you. So again, I'll just repeat. For first and foremost is for performing an experiment, you need to create a device. You should have certain device with you. So for creating any device, there are two ways to make the device. First is make a device in the GUI mode. Second is you can script it. You can just write a script and that script will be saved in the certain format of file format, and you can use that script to make a device. So whenever you will construct a device, that file will be saved in the .set format. These two are same. These two are same. The resultant of these two are same. Just the way of making is different. So if you make a device, that will be saved in the format of .set. Whatever the name you will give to your device, .set. And if you script it, it will be saved in the format of .scm. Whatever the script you write, it is. For example, I have made a diode. So diode.scm. If you are scripting it and if you are making it, it will be diode.set. So once you make a device, now you want to apply the physical models. There are many physical models present. So you want to apply any physical model to your device. So for applying any physical model to your device, you have to break the device into small blocks. That process is called meshing. So once you make a device, you have to break that device. Either you write it, script it, or make it. The resultant will be same. So after doing all that, either of the two process, you have to just break the device into small mesh. So that process is called meshing. Why are you breaking your device into small mesh? So that the numerical method equations or physical model equations should be applied properly to your device. So once you break your device into small blocks, that file, whatever the file after that, that will be created in the form of mesh.td. So if you are constructed the device and you have not created the mesh, that is not no use. You have to just create it into a small mesh, and the resultant of that will be mesh.tdi. And the resultant of that file will be mesh.tdi file. This we will see while performing the experiment. I'm just giving a brief overview. So once you have constructed a device and you have broken your device into small blocks, the resultant of these two files will be a mesh.tdi file. Now, once you have broken your device into small blocks, now you want to do the simulation of that device. So for doing the simulation, this mesh.tdr file should be input to this simulation software. That mesh.tdr file should be an input to your simulation software. So it will go through a CMD file. You have to just input this mesh.tdr file into a CMD file. So that CMD file is basically a simulation file, which will simulate your device. This will contains all the simulation information regarding the simulation. So your mesh.tdr file will be the input to the simulation file, and you will get the edge device simulation. Whatever the device you have created, it will be simulated. Now, after the simulation, you want to see the result. So for visualization of result, it will be using as usual. First stage is creating the device. Second stage is simulation of that device. And third stage is after the simulation, what are the results you got? So this will be done through the S visual. So results, there will be two files generated. That is design.plt and design.tdr. So for seeing the IV characteristics or CV characteristics of a device, that is current voltage relation or capacitance voltage relation, you have to look for the design.plt file. And if you want to see the device physics, that is band diagram, energy, electric energy potential, surface charge, electron concentration, hole concentration, for that you have to look for the design.tdr file. So this, as I told you, this tool is basically a file simulation software. Once you have all the files with you, it's very easy. But what are the changes to make in the files that you should do? So this is the basic energy flow diagram. Again, through different diagram, I'll explain you again. So these are the steps. Whatever I told you, once again, I'll just tell you through the two. Getting the device geometry and doping concentration. You have the device geometry means what is the size of your device and what is the doping concentration of your device. So this, if you know this, so this comes into the device, creating of device. So for creating the device, the software we will use is SDE. The software we will use is SDE. Once you create the device, I told you have to break that device into small grid or mesh for numerical computation. That is called SN mesh. So these two stages are pre-processing stage. That means you are just constructing your device. Once you have constructed your device, now you want to simulate that device. For simulating, that is applying the numerical equations, that is Poisson's equation. These are all physics-based equations which will be applied to your device. Current continuity equation, transport equation, small mesh you have created of your device, these equations will be applied to that mesh with certain boundary conditions. Now, once you apply these equations, you will be having some results. So for visualizing that results, you will use as visual. You will use again. Every time I'm telling you this because these are the basic steps of a to be followed while performing the experiment. So SDE is used to create the device. Once you create the device, you just break into small mesh, and the output of this will be mesh.tdr file. Output of this will be the mesh.tdr file. Now this mesh.tdr file is input to S device with CMD file. Using these two files, you will simulate your device. Once the device is simulated, there will be design.tdr file and design.plt file. I explained you design.plt file is for current and voltage relation. Design.tdr file is to see the band diagram, various device physics parameters like energy band diagram. What are the electron concentration, hole concentration, absolute electric field, energy, surface charge, all these parameters you can visualize using design.tdr file. And IV relations and CV relation you can visualize using design.plt file. So these are the basics which you will follow while doing the experiment. Zoom a little bit. Okay, I'll just zoom it again. So this is this I have explained you. These are the basic steps which we need to follow. First is to create the device. For creating the device, we will use SDE. Once the device is created, I told you there are two ways to create a device. Either you script it or you make it. Like you make any device, any structure in paint brush. Similarly, you have to make the device that format will be saved in the form of dot set. And if you are creating the device, if you are scripting the device, that will be saved in the format of .scm file. Then again, you have to break that device into small mesh or grid. Once you have broken your device into small mesh, then this simulation process will start. So simulation process, what is the simulation process? In this process, the whole physics, whatever the physics is there, that will be applied to your device. That is Poisson's equations, current continuity equation, transport equations on the well-defined mesh. Whatever the mesh you have created on that mesh, all these equations will be applied. Once all the equations will be applied to your device, there will be certain results out of that. Now that result you have to visualize. Whatever the output results are there, you have to visualize that result. That will be done through as visual or inspect. There are two tools to use that is as visual or inspect. These are the various formats of file which you will encounter mesh.tdr file, cmd file, design.plt file, design.tdr file in due course of time. So there is only one software, TCAD. In this, you will be learning the whole process, whole device simulation or fabrication process, how a device is simulated, constructed, simulated, and visualized. Now, I'll just how mesh.tdr file is obtained. Again, I told you na, in the software, I will tell you how mesh.tdr file is applied, but how what is that? I'll just tell you. Just that is once you have constructed a device, you just visualize you have constructed a PN junction diode. It is a rectangular shape. Now the whole size of your device is length is 100 nanometer and width is also 100 nanometer. It is a rectangle of 100 cross 100 dimensions. Now, for applying the physics-based equation, you just break that into small blocks. That I told you how it is done, visualize you. So once you break that device into small blocks by giving the certain commands, after that mesh.tdr file will be generated. If you are, many of you are from the Synopsys company, if you have the access to the tool that is good for you, you can use that access from your company laptop and you can perform the experiment. No problem. You are learning the Cadence and LT-Spice. This will be for your VLSI design and analog IC design experiment. You are having, I think, analog IC design and VLSI design subjects also in your in that curriculum. So for that, you are learning the Cadence and LT-Spice tools. So this is just I am giving an example of a PN junction diode. You can see this. This is a PN junction diode. I have just whenever you are designing any device, you have to just define the coordinate. The most important thing is you have to just define the coordinate. In which coordinate you are just designing the device. According to that coordinate, your device specifications will change. Your device specifications will change. For example, here I am using minus x and y coordinate, to design the device. Again, in the Synopsys TCAD tool, the default scale is in micrometer. The device default scale is in the micrometer. That is, if you write one, it will consider that is as a 1 micrometer. If you write 1, it will consider it as a 1 micrometer. Again, if you write 0.9, then it will consider it as a 0.9 micrometer or 900 nanometers That means 0.2. If you are writing 0.2, 0.2 will stand for 200 nanometers. 0.02 will stand for 20 nanometers. So this specification you should know. If it is 1, that means it is micrometer, 1 micrometer. If it is 0.9, that is, it is 900 nanometers. If it is 0.09, this is 90 nanometers. So here, if you can see this, I'm just right now I'm not explaining any experiment. I'm just explaining the coordinates, how it works in the coordinates for a tool. For example, it is going from in the minus x direction. It is going from minus 1.5 to minus 1. It is going from minus 1.5 to minus 1. That means the whole length of my device, the whole of length of my device is 500 nanometers. Because if you subtract minus 1 from 1.5, it will be 0.5. It will be 0.5. 0.5 means, as I already told you, 0.5 means 500 nanometers. So the length of my whole device is 500 nanometers. Out of that, it is divided into two parts. If you can see this, minus 1.25 exactly at the center. So this N side and this is P side. So my N side is 250 nanometers in length and my P side is 250 nanometers in length. So in this way, I can define my coordinates. In this way, I can define my coordinates. Again, this was the length of my device. If I consider the width of my device, it is, this point is 0. If I see this X and this is Y, this is X and this is Y, this point is 0 because it is exactly at the origin with respect to y-axis. It is exactly at the origin with respect to y-axis. And this point is 0.020. You can see this point is 0.020. 0.020 means 20 nanometers. 0.020 means 20 nanometers. So you can see that the width of my device is 20 nanometers. The width of my device is 20 nanometers. And you can visualize that the width is constant all across my device. All across my device. Here also, here also, here also. The width is constant, that is 20 nanometers. So if I say what is the size of my PN junction diode, it is 500 nanometers cross 20 nanometers. My specification of my PN junction diode is 500 nanometers cross 20 nanometers. Out of this, 250 nanometers is N region and 250 nanometers is P regions. So in this way, I can define the coordinates. In this way, I can define the coordinates. Again, I have applied to contacts also. I have applied to contacts also. If we can see this, there I have applied to contacts also of aluminium. The width, if you can see this, it is going from -1 to -990. It is going from -1 to -990. That means the length of my contacts is 10 nanometers. The length of my contacts is 10 nanometers. Again, width is same, 20 nanometers. Here also, I am going from minus 1.510 to -1.5. That is, if I subtract minus 1.510, this to that is 10 nanometers. Again, for N contact also, length is 10 nanometers. Width is all across the device constant 20 nanometers. So in this way, you can visualize the device. Instead of taking minus xy, if I have taken xy direction, so this instead of minus 1.5, this point would have changed. So this depends upon which type of axis you are taking to construct the device. So this I have just used to explain you how a coordinate system works for a device. If it is written 1, that means it is 1 micrometer. It is, if you subtract minus 1.5 to 1, that will come 0.5. If it is a 1 micrometer scale, then 0.5 is 500 nanometers. So you are asking what is meshing? So this is a, just consider this as a PN junction diode. So you can see this. I have broken my device into further into small rectangles. So this is just, this process is meshing. So here I have created the coarse mesh, that is the size of mesh is little bit larger. Here you can see this, the mesh is much finer. The mesh are much finer. Why it is like that? That I'll explain you while demonstrating the experiment. This is just the process how mesh is created. This region, the mesh is much finer. In this region, the mesh is much coarse. This I have told you. This again I have told. So I'll just go through this flow chart again once again. So first of all is you have to just create the device. For creating the device, you can use the GUI mode in which you can create the device. If you don't want, if you are not comfortable with creating the device, you can script that device also. You should know the exact coordinates, that is length, breadth of that device. You can just write the script of that device. Once you have done created the device, if you are creating it in the GUI mode, it will be .set file. If you are writing the script, it is .scm file. Once you have either of these two files, only one is required, then you can just create the mesh. You can just create the mesh. So output of this will be mesh.tdr file. This is the important file. This is the most important file, which will work as an input to the simulation software. Which will work in the input to the simulation software. So this mesh.tdr file will go to the simulation along with the CMD files. This you have to provide. This CMD file you have to provide. So that mesh.tdr file which is created from here and that CMD file which you will provide, simulation will take place. Once you simulate your device, you have to visualize that results. So the output of this simulation, there will be two files. There will be many files, but design.plt and design.tdr are the important files which are required. Design.plt file will be used to visualize the IV and CV relation, and design.tdr file will be used to see the Venn diagram, electric potential, surface charge, different device physics of the device. So this is the basic of a tool. I'll explain the coordinate once again. For coordination, I need to unmute you. So I'll just explain the coordinates once again. Then I will unmute you. If you have any doubts, you can ask that doubts also. So this is, I have to design a device. I have to design a device whose length is 500 nanometers, and whose width is 20 nanometers. The width of my device is 20 nanometers. So for that, you can take any coordinates. You can take any coordinate. It's not mandatory that you have to take minus xy, xy, whatever the coordinates you will take. According to their, your device specifications will change. Again, I'm telling you, if I would have taken it instead of minus xy, if I would have taken it yx, xy, then this device will shift here and the coordinates will change. So what I have done for every experiment, I have demonstrated you using different coordinates so that it can be, you can analyze all the coordinates. So here I have taken minus xy. Since it's not mandatory that you should start from minus 1.5. You can start from any point, but the difference between your start point and end point in this x direction should be 0.5. It should be 0.5. Since the specification is given that your device length should be 500 nanometers. So if I have started from minus 1.5, so 500 nanometers will come at minus 1. So this length I have specified it as minus 500 nanometers. Again, width is 20 nanometers. But if you can see this, it is starting from 0 and it is going from 0 to 0.020. I told you default scale is 1. If it is 1, that is 1 micrometer. So for 20 nanometers, it will be 0.020. It will be 0.020. That's why it is 0.020. And the width of my device is constant all across my device. You can visualize that it is constant all across my device, starting from 0 going to 20 nanometer, here also 0 to 20 nanometer, here also 0 to 20 nanometer. So x coordinate is changing, but the y coordinates is same for all the 3 points. Here also 20 nanometers, here also 20 nanometers, here also 20 nanometers. Again, I have defined two aluminum contacts also. I have defined 2 aluminum contacts also. So the length of the contacts is 10 nanometers. The length of contacts is 10 nanometers. So if you can see this point is, let me just zoom it. This point is minus 1.5. This point is minus 1.5. If I have to define a contact of 10 nanometers, so I should go 10 nanometers further in the minus x direction, further in the minus x direction. So if I go minus 10 nanometers further in the minus x direction, this point will be minus 1.510, minus 1.510. So this red portion is minus 1.510 because the length of my contacts are 10 nanometers. Instead, it was 5 nanometers. Agar it was not 10 nanometers, if it is 5 nanometers, then this point will be 505. Instead of 0.510, it will be 505. So this 10 nanometers is defining this contact. Similarly, here, this point is minus 1. I have to go further towards 0, So it will be 0.990. So this is again 10 nanometers. In this way, I can define the coordinates for my device. So I think mic, I have disabled the mics. If you have any doubt, you can ask.
Sir,
Yes.
I have one question. Why we have chosen minus x direction? Is there any reason to it?
No. I have told you, you can select any of the coordinates. If you
Okay.
select x, y, then you can start from 0 and you can go to 1.5.
Okay, fine. Okay. Understood.
This for first example, I have taken minus x, y. For second example, I will take x, y, so that it will be clear to you.
Understood. Okay.
Okay. Anything else?
So you mentioned, I mean, like for the coordinates, in between we have a junction, right? PN.
Yes.
First, we directly give the whole length, and then we decide a middle coordinates like that.
No. First, we will define the end region. We will start from minus 1.5 and we will go to minus 1.25. So that will be end region. Again, we go from minus 1.25 to minus 1. That will define our P region. Like that, we'll define. We'll see this.
Okay.
Anything else?
Sir, this coordinate will help to decide the technology in node, right? Like if it is
this will just tell you the whatever the length and whatever the technology you are working. Instead, if 500 nanometers, if I construct a MOSFET and I define the channel length as 18 nanometers, then the technology will be 18 nanometers, 10 nanometers. So that will define the technology, in which technology you are working. Anything else? Okay, so I'll just go to the tool. So if you have there were any labs before this VLSI design, you have any labs before this? This is your first lab, or you have in this
No,
session
we
you have
have
any?
analog IC design lab.
So you know how to access that tool portal, OSHA portal, BITS
OSHA
portal.
portal,
Sir,
yes.
if you can
Yes.
explain again.
Okay. I'll just explain you again. So what you have to do, you have to just let BITS OSHA. If you will just click here, this is the first thing. You just click here. So like this, you will get all the interfaces. These are from the previous semester. In the 2 to 3 days, you will see your MOS device and micro fabrication for your NSP4 here. You just select that MOS device Whatever the slot you want to book, you just click here. You just can select the date, 9, slot timing, which slot timing you want, and you can just book the slot. You can just book the slot. Once you book the slot, before the time it will be light blue. And once that time reaches for which you have booked the slot, it will become dark blue. So you can just click on that, connect, and it will show you like this. So you have to just click here. Don't click here down. You have to just click here to connect to that Red Hat. So once this Red Hat is open, you can just go to activities and files. From here, the main thing is which I want to explain you. So right now you are seeing this TCAT folders. This TCAT folder you are seeing here, but it will not be there for you. It will not be there for you. You have to just copy it from the home. You have to just copy this TCAT folder from the home folder. Since I have already copied this TCAT folder from my home folder, that's why I am able to see it in my account. But for you, you need to copy this TCAT folder. Again, whatever the files I'll give you for the furthermore in the simulation, for which will be needed for you for the simulation, I'll paste it in that TCAT folder. So don't get confused. Ki, sir, you told that you have pasted that file in the TCAT folder, but it is not visible in my TCAT folder. It will not be visible because this TCAT folder you have already copied. Now, whatever the files I have shared after your copying will not be there. So again, if you want to access any file which is not in your this TCAT folder, you have to again go to the home, and from home you need to copy this file. I'll tell you how to do that. So assume that there is no TCAT folder here. You need some files to run the software, but this TCAT folder is not there. So what you have to do, once you open the files, activities, in activities open files. Now type Control L. You have to type Control L. And here you have to type etc backslash skel backslash etc backslash skel backslash and press enter. Control L backslash etc backslash skel backslash enter. Now, after that, you will find this TCAT folder here. You can find this TCAT folder here. So just copy it, copy, go to your home folder, and you can paste it here. Got my point? Just right click and paste it here. Since there is all one TCAT folder is there, so I will not paste it. You have to paste it here. So what are the important files you will need will be there in the TCAT folder. This TCAT folder will have all the necessary files which are required to simulate the experiments. So again, for example, initially there were only 4 folders in the TCAT file. For example, this IMP folder is not there. This IMP folder is not. So, but some files are there. This file is there. So you need this file. So you will tell, sir, this IMP folder is not in my TCAT folder. It is there in your TCAT folders. So that means I have posted this folder after you copied that folder from the home folder. So for that, you have to again go to backslash etc backslash skel. From there, you will find that file, whatever file I have shared after you copying the folder. So is that clear?
Yes, sir.
So whatever the necessary files will be there, that will be in the TCAT folder. For copying any files in the TCAT folder, you just type that command. I'll share that script, lab manual also, where all the scripts are written. So you just follow that scripts and you can copy that. Now this tcat folder, the most important file is this setup.tcat.csh. This file is very, very much important. If this file is not there in your working folder, you will not be able to access the tool. Whatever the experiment you are performing, this setup.tcat.csh file should be there in your working folder. For example, if I'll create one folder here, new folder, lab1, lab1. I created one folder with the name lab1. So right now it's empty, nothing is there. So I'll just open the tool. So these are the process which will be needing, you will need to perform all the process. What? Open Red Hat Enterprises, go to activities file, go to home, press Ctrl L, type etc /SQL, press enter, then tcat folder will be visible. You have to just copy that tcat folder. Again, this setup.tcat.css file, this is very important file, that file which I have told you. If you don't copy this file in your working folder, you will not be able to simulate the tool. You will not be able to simulate the tool.
Sir, if we are working in that office laptop, then also we need to do this tcat.
No, then this is just to access the tool. That's why because these tools are saved in the server now. So for here only you need to follow this instruction. If you are using your own access to the tool, if you have the access to the tool directly from your company, then you don't need to follow these steps.
Okay, then directly open terminal.
Directly, no need to open the terminal also. You can just open the, you can just open that tcat, that is SD window. I'll show you from where you can do it.
Okay, okay, sir.
So this is my folder which I have created. Since I have to copy this file there, I'll just copy this file. I'll paste it here. If this file is not there, you will not be access the tool. You will not be able to access the tool. Now, once you have copied this, you have to type certain commands. You have to type certain commands, that too in the terminal. So for that, you just open in a terminal. First command is tcsh. First command is tcsh. Press enter. Second command is, I have to see that command. First command is tcss. Second command is source dot source source space setup slash tcad dot csh. One, you have to type once. If you type once, then it will come automatically come. For this, since I am using it for first time and you will also use first time, you have to type it. After that, you don't need to type it. You will get it directly. Enter. Now you can access the tool. Now you can access the tool. So these commands are necessary to access the tool. So once you type this command, now you can access the tool. Before this, you can't be able to access the tool. TCSH source setup slash tcad.csh. These are the two commands which are need to access the tool. And this setup file is there, should be there in your working folder. Now I told you there are two ways to construct the device. There are two ways to construct the device. First is using SDE, where the GUI mode will be there. And second is you can script the file. So today I'll just demonstrate you how to create the device in the GUI mode. So for creating the device, the tool is SDE. So just type SDE and press it. So this GUI mode has been, this mode will be, this mode will be open. Again, I will tell you, I'll just share that PDF with you where all the instructions have been written. For accessing the tool, whatever the working folder is there, you have to copy that setup.tcsh file. Without that, you will not be able to access the tool. Then these two commands, tcsh, then source setup /tcsh. These two commands you have to type. Then you can access the tool. Then you can access the tool. Then I have typed the SDE command. So this is my GUI mode where I can construct the device. So for constructing any device, what we need? First, we need the dimensions of that device. What are the dimensions for that device? Second, what we need? What is the doping material which we are using? For example, once we create the device, it will be pure silicon. Pure silicon will be there. So we want to make it P-type or N-type semiconductor. We want to make it P-type pentavalent impurity or trivalent. We want to add pentavalent or trivalent impurity so that make it P-type or N-type semiconductor. So which type of impurity and what is the concentration of that impurity that we should do? And third, what are the size of contacts we need to place? What is the size of contacts we need to place? In some of the experiments, you need some extra aluminum in the contacts. In some of the experiments, you directly place the contacts over silicon. That depends. If you can't, you can place the contact directly over the silicon. And in some cases, what you need a thin layer of aluminum, that is metal, between the before placing the contact, so that proper isolation should be there. So that we can see how we can do both the, how we can use both the ways we can. So this is the interface. I'll just briefly describe. So from here you can select the material. There are many various material which we use to construct the device. So from here, drop down list, you can select any material. Right now, we are using silicon. We'll use a pure silicon. So silicon is selected. For different cases, you can go through the different types of materials available and you can select different type of material from this drop down list. From here, you can apply the contacts. How to do this, I'll just explain in 2 to 3 minutes. From here, you can apply the contacts. From here, you can change the mode, in which mode you want to use that. Here, you can what are the coordinates you want to apply, you can just do it. So all these things I have written here. I have just written here. You can go through this. With the video will also be recorded, and you can just go through this also. From up to here, I have told you, you just type SD, that GUI mode will open. So creating the structure in SD window. How to create the structure in SD window? I have just written everything. First, type SD. In SD, go to view. In view, go to GUI mode and make it 2D. So you can make a 2D device also or 3D device also. In this TCAD, you can make a 2D device also and 3D device also. So right now we are making a 2D device. So you have to make it a 2D mode. Then disable auto region naming. Then apply exact coordinates. Then these coordinates x minus y, you can, as I told you, you can select any coordinates. You want to select x minus y, you can select x minus y. If you want to select minus xy. So which coordinate you select, accordingly you have to give the value of that coordinate. According to that, you have to give the value of that coordinate. That I will explain you how you can do. Then from the materials, you have to select the material. As I told you, there are several materials. From there you can silicon. So in this way, I'll just demonstrate you how to construct the device. These are the various steps you can follow. These are the various steps you can follow to construct the device. Then after constructing the device, you need to set the context. You need to place the context. That also I'll show you how to place the context. Then doping. Say, I told you that you have taken a pure silicon, but it is divided into two regions, N region and P region. So you have to place the doping also. So how to do that? So now I'll just go through each and every steps. So first step was you have to go, first of all, you have to make a 2D. The view should be 2D. So what I'll do, I'll go to view. Here in the GUI mode, I'll make it 2D. By default, it will be 3D. By default, it will be 3D. You have to make it 2D. So what I'll do, I'll make it a 2D. Then again, I go to draw. I'll just disable this auto region naming. What it will do, it will automatically name your region, but you don't want automatically your region to be named. You want to name your region by yourself. So I'll just disable D. And again, I will go to draw and I'll select the exact coordinates. So first view, make it 3D to 2D, draw, go to exact coordinates, disable exact coordinates, and third, just select the exact coordinates. Now, as you know, the shape of your device was a rectangle. If you know that the shape of your PN junction diode is rectangle. So what I'll do, I'll just select a rectangle from here. I'll just select a rectangle, and anywhere I'll just draw a rectangle. Okay. Again, this material, don't forget to select the material from here. Since by default it was silicon here, that's why I have not selected the material. But if you are using any other material, for example, instead of silicon, you are using germanium, then you have to select germanium from here. Now, this is the main coordinates. The way you will define the coordinate here will define your axis. For example, let us say, if I'll make it 0.
Sir, from where did you get exact coordinates? Can you please show again?
Again, I'll tell you. Once you just select the rectangular shape from here and create a rectangle anywhere on the screen, this window will automatically pop up. Once you create the rectangle, this window will automatically pop up. Now, you should know the size of your device. So, and again, I told you, if I write 1 here, that means 1 micrometer. It specifies that it is 1 micrometer. So that means if I write 0 here, I'll write 0 here. And if I'll write 0.250, 0.250, that means I'm starting from 0 and I'm going from to 0.0250. That means 250 nanometers. That means I'm going in the 250 nanometers. And in which direction? If you can see this, I'm going in which direction? It is positive X direction. It is positive X direction. Instead, if I'll give a minus here, if I'll give a minus here, then it will be a negative X direction. That means I am selecting a minus X coordinate. I am selecting a minus X coordinates. Instead of selecting a positive X coordinate, I have selected a minus X coordinate. Again, Y direction. If I like from 0, and if I go into 0.020, that means 20 nanometers. That means 20 nanometers. If I'll make it minus, that means it is negative X direction. That means this is negative X direction. I have to select X minus Y coordinate. I have to select X minus Y coordinate. I'll press OK. So out of 500 nanometers device, my whole device is 500 nanometers. 250 is P region and 250 is N region. First region I am defining is my N region, whose length is 250 nanometers and width is 20 nanometers. So I'll just make it region N. I'll just give it name N and I'll just press OK. Now from here, if you can see, there are many axes, X axis, Y minus X minus Y axis. So the axis which I select, according to that, it will align. So I'll just select XY axis. So this is XY axis. So this is my P region. Length is, this point is 0, 0. This is 250 nanometers in X direction and 20 nanometers in Y direction. I have defined my N region. Again, what I have to do? I have to define my P region. So what I'll do, again, I'll make a rectangle, and you can make rectangle anywhere in your GUI. I'll just make a rectangle here. So where will my, in the X direction, where will my P region will start? Exactly where my N region is ending. Where my N region is ending. So my N region was ending at 250 nanometers. It was ending at 250 nanometers. So it will start from 250. It will start from 250 and it will go to, because the length of my whole device is 500 nanometers, so it will go to 0.50C, 0.50C. Again, while defining the coordinates, I told you that the width of my whole device is constant. My width of my whole device is constant. So it will be 0, 0, 0 to 0.0 to 0.020. So my P region is starting from 0.0250 and going to 0.0500, and the width is constant, that is 20 nanometers, 20. So I'll just press OK. Again, the region is I'll press OK. So this is, in this way, I got my N region and my P region. I got my N region and my P region. Now, this is not N and P region until I apply a doping to it. Until I apply to doping it. Before applying to doping it, it is just a pure silicon wafer. It's a pure silicon wafer. So I have to just apply the doping to it. So for applying doping, you have to go to just device. There is one option of device. So just, if you just click on the device, first option is constant profile placement. You have to just select that constant profile placement. So here, if you can see, you have to just select the region. You have to just select the region. So there are two regions. When I defined my device, I have defined two regions. That is region N. So when here region N is defined, then it will be orange. If I'll go here and I'll make it P, then this region will be highlighted. This region will be highlighted. So this is just to show that which region you are doping. So first I'll dope N region. I'll just make it n. I'll make it n. You can make it 1 also. You can keep it 1 also. Don't need to change. If you want to change, you can change this to n. Here region n. Here also, you can just make it n if you want. If you don't want to. And if it is n, the concentration is not boron. It is for P. For n, you have to make it phosphorus. So you just search for phosphorus. So you have selected doping material as phosphorus. And what should be the concentration? What should be the doping concentration? Either it should be 1 e to the power 18, 1 e to the power 19, 1 e to the, that you have to decide what should be the doping concentration. I'll just make it 1 e 19. I'll just make the concentration as 1 e 19. There is one option since I'm demonstrating in the small screen, not seeing that option of how to do it. Just wait for this. Just close this device. And sorry for the disturbance. I'm using someone else's laptop. That's why it's not that full screen is not coming. So I'll today just leave it. I'll just demonstrate you using the SCM file today. Tomorrow I'll just demonstrate in the next class. I'll just demonstrate you how to create the device. Since it's creating a problem, I'll just demonstrate you how to write an script file. So for that,
I'm opening, sir, in my office laptop, but it is not opening. I have done module load Centeris, then SD I'm typing, it is not opening. It is telling something error, tcat current Linux something.
no,
like
you are using that license provided by the institute, or you're using your own license,
Mm.
whatever the company
My
has
office
provided.
company has provided.
I'll just look it into it. Right now, I'll just demonstrate you using the scripting file. In the next class, I'll just demonstrate you using this. For that, I'll just copy this pn junction tag dgt.sc. This is same. So I told you either you can construct a device or you can script the file. So you can script that command. So here what I have done, I have just scripted that command. So I'll just copy this file in my working folder. And then I'll just explain you this file. Paste. So if I'll open this file, so this is a script. Whatever I was constructing and whatever structure I have told you, instead of constructing it, I have just scripted it. So I'll just explain you each and every step. That SCM file, if you have any one SCM file, for example, if you have the SCM file of a diode, if I provide you the SCM file of a diode, you can script it, you can make the changes in the script, and you can make it for a MOSFET or for a double gate MOSFET or for any other device. You just need a one basic SCM file. So this is the diode SCM file for a diode. This is a scripted file for a diode. So as I told you, there will be 4 regions in the diode. I'll just explain you through that structure, whatever the structure was there. It has 4 regions, 2 aluminum regions, 2 aluminum contacts at the end, and 2 N, one N and an P region. There are total 4 regions in this PN junction diode. So whatever the coordinates are here, I have just scripted it. So first region is my P region. I have constructed my first region as P region. So it is 250 nanometers. Its width is 250 nanometers. Length is 250 nanometers. So it is starting from minus 1.5 and it is going to minus 1.250. That means this is 250 nanometers. And the width is 20 nanometers. So in the Y coordinates, it is 0.020 from 000 to 0.020. That means the width of my device is 20 nanometers. The Z coordinates for all the 4 regions will be 0 because it's a 2D device. It's a 2D device. There is no 3D region here. So it is 000. For all the 4 regions, you can see Z coordinates is 000. So my first region is P region, which is of silicon, which is starting from minus 1.50 and it is going to minus 1.250. That means 250 nanometers length, and 000 to 0.020, that is 20 nanometers width. Now, where my P region is ending, from there my N region will start. So you can see this, it is ending at minus 1.25. So my N region is starting from minus 1.25 and it is ending to minus 1. It is ending to minus 1. Since the width is constant, 000 to 0.0, this will define my silicon region, that is N region. Material which I am using here, it is silicon. Material which I am using here, it is also silicon. Again, now I have to create 2 contacts. So P contact will be just 10 nanometers towards P region. So P region is at minus 1.5. So my P contact will start from minus 1.510 and it will go end to minus 1.5. This is my P contact. The width of contacts is also same. The width of contacts is also, you can see this again 20 nanometers. This is 20 nanometers. So this will not change. So this is 0.000 to 0.020. Here also 0.00, 0.020, and n contact will be right side of n. So it's starting from minus 1.000 and it is going to minus 0.990. You can see this. It is going from -1 and it is going to minus 0.990. This is made of aluminum. So here I have to select the material aluminum. So this will define my whole device. For example, these two regions are made up of silicon and these two regions of contacts are made up of aluminum. Again, I have to give name to my contacts. Whatever the contacts are there, I have to give the name to that contact. For contact, you can give any name. Here I have given the name P side and N side. You can give P contact, you give whatever name you want to give, you can give by it's your choice. Whatever the name you want to give, you can give that name. I have given name for P contact, I have given name P side, and for my N contact, I have given name N side. And according to our WebGeo RGB, you have to select the color of your contact. In the GUI mode, you can go and select the color. Here you have to just script it. So 001, I have scripted it 001. It will resemble some color in the WebGeo RGB, some color. This is some color in the RGB. Similarly, 010 will be some color which will be of N side. So this is just the color of your contacts and this is the name of your contact. Now again, where this is contact setting, where you want to place your contact, where you want to place the contact. So in the X coordinate, it is, if you can see here, this is your contact. Once you have put an aluminum layer after your silicon, you need to place the contact. So these two tiny wires, if you can see this, these two tiny wires are contacts. So if you can visualize, it is in the X direction, it is exactly where the aluminum layer is ending. It is exactly where the aluminum layer is ending. You can visualize this. And for Y region, it is exactly at the center. For if you, this is Y axis, it is exactly at the center. It is exactly at the center. So if you can see here, for X, it is exactly where my aluminum is ending. For this, it is ending at 510. And for this, it is ending at 990. For N side, it is ending at 990. And for P side, it is ending at 510. Now, since the whole width of my device is 20 nanometers, you have seen that the width of my whole P device is 20 nanometers. So exactly at the center will be 10 nanometers. So my contact setting, this is 10 nanometers, this is 10 nanometers. So if you can see this point, this is 20 nanometers. So it is exactly at the center, that is at 10. Now, again, I'll go here. It is clear. Up to here, it is clear. First, I scripted my regions. Whatever the regions present in my device, there are 4 regions. 2 are silicon region, 2 are metal regions. Then I gave the names to my contacts. For P side, contact name is P, contact to P is P side, contact name to N is N side. I have defined the color for it also. Then I have set that contact. Proper placement. It is exactly at the center. Now this is the doping. This is the doping. So for P side, doping is boron. Whatever the doping material we are using at, this is boron. This is boron. And this is the doping value. You can change this value also. For example, instead of 1E17, you can make it 1E18 also. That depends upon you. So on the P side, you are doping with the boron and the doping value is 1E18. And for the N side, you are doping it with the phosphorus. Again, you can change the value of doping concentration. Instead of 1E17, I can make it 1E18. Whatever you want to make it. So this is just the doping. In this region, you have add the doping to your P side and N side. P side is boron, N side is phosphorus. Now comes the main part. Please focus on that. This is the main part. So meshing means breaking your device into small parts, making your device into small parts. So this is the refinement size you have given. That means the size of each and small piece is 0.005 in the X direction and in the Y direction, and 0.02. That means that size of rectangle is 0.005 and 0.002. This is the size of the small rectangle in which you are breaking your device. 0.005 means 5 nanometers, 0.002 means 2 nanometers. That means the size of your small mesh is 5 nanometers by 2 nanometers. So why you are breaking the device into small mesh, that I have told you. So for applying the simulation Poisson's equations and very current continuity equation, you need to divide your whole device into small grids or mesh. That's why you are breaking your device into small mesh. So this command is just showing that you have broken your device into small mesh. Again,
sir,
before breaking the mesh, yes.
So this meshing defines the size of the device. When we say 2 nanometer or 3 nanometer device, this is because of this.
I'll just tell you this defines this size. I'll just open that. This meshing defines the size of this red rectangle you are seeing here. These green rectangles. These are this size is that mesh size. This is the size of complete device, which is 500 cross 220 nanometers. Now I have broken my device into small mesh.
So we can say our device is 20 nanometer device.
Our device width is 20 nanometers and length is 500 nanometers. This length is 500 nanometers and this width is 20 nanometers. So for this device, for applying the physics equations, I have to just break my device into small mesh. So this meshing size, this is the size. This size you can change. Whatever the more fine you will make your mesh, the more proper results you will get. So meshing is just to apply the physics-based equation to your device. So the more finer will be the mesh, the more properly you will get the results. There is the advantage of also mesh is that you will get the more fine results. But the disadvantage is that if you break your device into more fine mesh, it will take lots of time to converge. Converging time will increase. So you have to just make
your voice is low.
So I just want to tell that the meshing size is just to tell that the more fine will be the mesh, the more finer will be the mesh, the more accurate results you will get. But if you make the mesh more finer, then the simulation time will be more. So there is a trade-off between the size of mesh. So you pick the size of mesh such that you get the proper results also, plus it will take less amount of time to simulate also. So in this way, we define the size of the mesh. Meshing size means in which the more fine, how much finer you are breaking your device into small blocks. So this is the fineness. Now why I have made the course that this the size of mesh more large here and smaller here, that I'll explain in the next step. You can see this. This is the depletion. This is exactly the junction. This is exactly junction of PN junction diode. So near the junction, I have made the mesh more finer. And outside the junction, but inside the device, as we are going away from the junction, the size of the mesh is larger. Why I have made it, that I'll explain you in the next step. First of all, you should know why we are breaking our device into small meshes. So the only thing we are breaking our device in the small mesh is that we will apply the physics-based equation, that is Poisson's equations and current continuity equation to our device. So the more finer will be the mesh, the more accurate results you will get. Again, the trade-off is that if you make the mesh too much finer, then it will take lots of time to converge. So you have to just set the mesh accordingly so that it will take less time and you will get more accurate results. Now, again, for creating the mesh, you have to just define a rectangle such that it should cover our whole device. So there should be a rectangle for creating the mesh. Before creating the mesh, you should make a rectangle that should cover our whole device. So in the GUI mode, I have told you that just scroll your mouse such that make a rectangle such that it should cover our whole rectangle. Whatever the device is there, make a rectangle which should cover our whole device. But here, since I am just telling you with the scripting, so we have defined a rectangle here. You can see the rectangle. The dimensions of this rectangle is such that it is larger than our device. This is defining a rectangle which is larger than our rectangle. Whatever the size of our device is there. So this rectangle is such that it is larger than our rectangle. So this we need to do. Before meshing our device, we need to just define it. We need to just, it is a way of selecting the whole device. We are selecting the whole device where we want to apply the meshing, which region we want to apply the meshing. So we want to apply the meshing in our device. For that, we have to select our device. So for selecting a device, what we do, for selecting anything, what we do, we make a scroll our mouse and we make a rectangle which covers our whole device. So here, this rectangle is positioned such that it is covering our whole device. So the dimensions of this, you can see this, our device size is from 0 to 20. In the Y direction, our device size is 0 to 20. You all know that. So the rectangle which is covering our device, it is minus 20. That means 0 is our starting from of our device, and it is minus 20. That means this rectangle is normally bigger than our normal rectangle. And here, instead, our device is ending at 20, and this rectangle is 40. That means again it is covering our device in this direction. So that means the rectangle, whatever the rectangle you have made, it should cover our whole device. Again, this is, you can see this here, the meshing size is larger as compared to this. This is again optional. This is again optional. This step is optional. You want to include, if you want more finer results, you can include this steps. If you don't want more fine results, you can skip this step also. This is multi-box, means this rectangle is covering our whole device. This rectangle is covering our whole device. And this rectangle, as I told you, in some region, I want the mesh to be more finer. In some region, I want the mesh to be much finer. Here, near the junction, I need the mesh to be more finer. So this is completely optional according to your results, whatever results you want. So if you want more accurate results, so you know that most of the operation in a diode takes place across the junction. So you need to concentrate more near the junction. If you consider a MOSFET, most of the operation takes place near the channel of the MOSFET. So you need to concentrate more near the channel. Similarly, for a PN junction diode, most of the operation takes place near the junction. So if you make the mesh more finer near the junction and the mesh more coarse away from the junction, it is fine. That's why I have defined one more multi-box. And in that multi-box, I have made the mesh more finer. So if you can see this, here in this multi-box, here the size of mesh is 0.005, 0.002. Here the size of mesh is 0.002, 0.001. More finer than the whole device. And if you can see the coordinates of this multi-box, if you plot this, you will find this box is defining the region near the channel. This box is defining the region near the channel. Now, in this format, you save your model, whatever the name you want to give. Here, I have given the name DGT. You can give any name to your SCM file. I have given the name DGT. This is the name given by me. You can give the name diode. You can give any name to this. So again, I'll explain you. In the first part of the scripting, I just scripted the coordinates of my device plus the material I have used to define the region. In the second part, I have just given the name to my contacts, P side and N side. These are named to my contacts. This name is up to you. Whatever name you want to give, you can give. This is the color of my contact. 001 is some color in the VibGyor. Similarly, 010 is some color in the VibGyor. So accordingly, that color will be set to my contact. Again, where I want to place the contact setting, this I have defined, it will be exactly at the center. So 20 nanometers is my device. So it is 10 nanometers. That means exactly at the center and it at the end of my aluminum region. After placing the contacts, I have added the doping. P side, I have added the doping of boron, 1 e to the power 18. And on the N side, I have added the phosphorus with the doping of 1 e to the power 18. Again, this is up to you. You can change the doping concentration. Once you constructed the device, now you want to break your device into small mesh. For breaking the mesh, you have to select that whole device. For selecting a whole device, I have defined one rectangle, which is just greater than my rectangle. Whatever the device size is there, this rectangle is just greater than this device size. And this is the size of the mesh. Again, this is optional multi-box. If you want some more refinement in your device, you can define a region where the operation is more.
Sir, can you please explain the mesh size again?
Mesh size means.
I'll just how did you define it?
I'll just explain this.
Yes, the coordinates I am talking about, sir. Concept I understand.
So first of all, I have defined a rectangle which is covering my whole device. If you draw this rectangle across your device, you will find this will converge into a rectangle which is just greater than our device. After defining this rectangle, I have given the mesh size. How fine my mesh should be. If I'll give it 0. I can change the size here also. If I want my mesh size to be 0.05, instead of 0.05, I want the mesh size to be 0.01. 0.01, that means my mesh is not that much fine. So this is the size of my mesh. Mesh means by how much small margin you are breaking your device. 0.005 means that is 5 nanometers of size. Whatever the smallest mesh is, that is 5 nanometers. And 0.002, that means the range of your meshing size is between 2 nanometers and 5 nanometers. Minimum value is 2 nanometers, maximum value is 5 nanometers. That means whole 500 nanometers device is broken into 5 nanometers and 2 nanometers small rectangles like this. This. So it is just showing there are only 7 rectangles because I can't. So this 500 nanometers is divided into small rectangles of 5 nanometers. If you are defining the 5 nanometer size and total size is 500 nanometers, that means there will be 100 such rectangles. These rectangles will be 100. You understand?
Yes, sir.
If you're making the size of mesh is 10 nanometers, then total number of rectangles will be 50. If you are making the size of your mesh to 1 nanometers, then total number of rectangles will be 500. So it is just the way you are breaking your device into small blocks. So the more finer will be the blocks, the more accurate will be the result. So instead of making finer blocks all around the device, what I did near the junctions, as we know that the most of the operation took place near the junction. So what I did, I make the mesh more finer across the junction, and at the away from the junction, the mesh is not that much fine. So this is my SCM file. So this is my working folder. Here I have copied that setup file plus SCM file. Now I have to open this file. Since this is a scripted file, I need to open this file. So if I'll show you. Here, I'm going step by step so that it should be clear. I have this SCM file. If I'll open this SCM file, the output in output, this mesh.tdr file should generate. It should generate. So once I open this SCM file, this mesh.tdr file should generate. So I'll just open this mesh SCM file, and the output should be mesh.tdr file. So I'll just open this file. For this, again, right click, open in terminal, tcsh, enter. Setup. SOU source. Space. Enter. Formal. Now SDE. Here I need to open that file. So what I'll do, file. Here you have to select open model. You have to select go to file, open model. So once you do the open model, you will not see your SCM file here. You will not be able to see your SCM file here. For that, you have to go here and make it scheme files. You have to make it scheme files. Now you will see your SCM file here. Now you will see your SCM file. Just select it, and so once you open your SCM file, now you can close this. You can see this. Initially, there was only one file, dgt.scm. Now these much files has been created, and you are much interested in that mesh.tdr file, whether it is created or not. So you can see this, that dgt mesh.tdr file has been created. This file has been created. That means whatever the SCM file you have made, it is right only. It is right only. So just close it for I need to explain. So initially there were only two files. This setup file, which is necessary to remove the tool. This SCM file, whatever the scripting you have done. Once you open this SCM file, this number of files are generated, and you are interested in that mesh.tdr. It is generated. That means it is fine. Now, again, come here. Now, for simulation, what you need, you have mesh.tdr file with you. Now you need CMD file. What you need? CMD file. CMD file contains all the physics-based equations which you need. So if you can see this, there is no CMD file. I need CMD file. So if you go to TCAD folder, you will find that there is one CMD file. There is one CMD file. So you need to just copy this CMD file. Go to your lab 1 folder. Yes. Now CMD file is there. Now mesh.tdr file is there, and CMD file is there. Now you can simulate your device. Now you can simulate your device. So again, open in terminal.
What is there in this CMD file?
I'll just tell you. Once I'll just simulate it. Okay, I'll just first explain that CMD file to you. So as I told you, all the simulation steps, whatever the simulation steps are there, it should be there in that CMD file. It should be there in the CMD file. So first of all, the input for the CMD file will be the mesh.tdr file, whatever the mesh.tdr file. Here the mesh.tdr file name is PN diode. So it will not simulate. You have to give the input name of whatever the mesh.tdr file you have generated. So what is the name of your TDR file? It is DGT. So first change, whatever you have to make sure that since CMD file, the input is mesh.tdr file. So whatever the mesh.tdr file you will give input to it, only that file will simulate. So the mesh.tdr name of your file is not PN junction diode. You have to just change the name here. In all this.
Every time we need to create this CMD file, or this is a constant?
No, it is there. I have given you. I will give you this CMD file.
No, but if
you have to change it according to your device. For example, if it is a MOSFET,
other parameter will remain same. We only need to change the grid, right?
Grid will change, context will change, like that. Something will change. Now, if you can see this, the contact name, whatever I have given in the SCM file is P side and N side, and here name is P contact and N contact. So I need to change the name here also. Make sure that the name of contact should be same on both the files. It should not change. If it is P contact and N contact here, it should be P contact and N contact on the SCM. Or if it is P side or N side, the name should be same both. So what I'll do, I'll change name here. P side N side. So make sure that the contact name should be same. Here also, it should be TGT. Again, wherever P contact and contact is there, you have to change the name. Here P contact inside. Okay. Now what is there in these are all the equations. These are all the equations. These are all physics-based equations. Now, what you are doing? You are increasing your P voltage. That means you are gradually.
We need to rewrite these equations for every assignment we are going to do, or this is
this file only you need to change this context. You need to change these values. These equations are already written. You have to just change the whatever the specific. For example, if it is 3 contact device, then you have to make, instead of 2 contacts, you have to make 3 contacts. In course of time, you will get to know. Again, what we are doing, we are increasing our P voltage from 0 and we are going up to 1 volt. That means we are increasing our P voltage from 0, 0.1, 0.2, 0.3, and we are going up to 1 volt. And what we are plotting the current, how the current is changing when we are gradually increasing our P voltage. So save it and close it. Now we have CMD file with us. We have SCVM mesh.tdr file with us. Now we want to simulate the device. So PCSS source.ct setup. So command for simulating the device is sdevice. The command for simulating the device is sdevice. So sdevice. And whatever the name of your CMD file is, the name of my CMD file is pn shift underscore diode 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 shift underscore des dot cmd. So whatever the name sdevice followed by the name of your CMD file. You can give the name of your CMD file any name you can give. Here the name is pn underscore diode underscore des dot cmd. Again, in the what change I have told you, the name of contact should be same in the SCM file and CMD file. Again, the input to that is mesh.tdr file. Mesh.tdr file. Here the name of mesh.tdr file is DGT. So make it DGT. Now press. So now the simulation is So after the simulation is done, now you want to visualize your results. So again, I am comparing it with the flowchart so that you can be able to understand once the simulation is done. Now, once the simulation is done, you can visualize the result with as visual. You can visualize the result with as visual. You have to search for only two files. One is design.plt file and second is design.tdr file. If it is generated, that means your simulation is done. Design.plt and design.tdr file. So in the first experiment, we will look for the design.plt file, whether it is generated or both files will be generated, but we will go detail into design.plt file. So I'll just go to the tool again. The command for visualization is result is as visual, enter. Now what I told you, we have to search for design.plt file. So this is id design.plt file. Don't search for initial, search for whatever the name you have given, tgt_design.plt. So you have to search for this file, whether this is generated. Again, search for design.tdr file, whether it is there or not. So you can see the design.tdr file is also there. What I'll do, I'll just open the design.plt file, open. What I have done, I have given the voltage from P side and I have measured the current. So what I'll do, I'll just say P side, outer voltage that I'll plot in x-axis. From P side, I can measure the total current in right axis. So you can see this. Today, this is. So if this is the current plot, this is the IV current plot which you will get. So what you did, you just search for design.plt file. In design.plt file, you just select the P side. You will see your design.plt file. Go to P side, outer voltage in x-axis. Again, P side, total current in right y-axis. I'll again plot it. P side, outer voltage x-axis. P side, total current right y-axis. So this is your IV characteristics of a PN junction diode that is in the forward bias. So what you have to do, this is the condition for a forward bias. Similarly, if I'll make instead of 1, if I'll make it -1 or -2, then it will become a reverse bias. You can change it. Instead of making it up 1, if you can make it -1 or -2, then it will work as a reverse bias. So in the first experiment, what you have to do, you have to just plot the graph for forward bias and reverse bias of a PN junction diode. Any doubt regarding that? Any doubt?
Sir, one
sir.
small one. In the can you open the script of the device? In this, I understood the coordinates, but what is 990 and that in the y direction I didn't get. In the x direction I got it, but
In the y
-1 to 990.
This is
in the
x
diagram
direction.
you showed.
I'll just show the diagram and I'll just compare it there from there. So
Yes.
if you can see this, I'll just zoom it.
Hmm.
This is -1.5. Got it? This point is -1.5
Okay.
in the x direction. Don't see y direction now. This point is -1.
Hmm.
Now I want to put a contact of 10 nanometers. Okay.
Okay.
So if I'll go 10 nanometers from -1 to this direction, what will be the point? 0.990.
Okay.
Similarly, if I'll go from -1.5 to 10 nanometers this direction, this will be -510.
Okay.
But if you can see this, what is the change between this and this red part and this whole part? What is the change? Only change in the length. If you can see the width of this, both the regions are same.
Yes.
In the y direction, both the regions are same.
Only 10 got increased.
10, that too in the x direction. Y
Exactly.
direction there is same. So if you can see script, y direction is same. Only x direction, for in the p side it is increased by 10. In the n side it is decreased by 10, because in the x direction we are going towards 0, and in the y direction we are going away from 0. Oh, in the p side we are going away from 0.
In the place of minus 990, can't we go? I mean, like towards the 0, right? Why
This
to
is 10
mention like-
nanometers. If you can, if you subtract 990 from 1,
Okay,
it is 10
okay.
nanometers.
Yeah, right.
Got it?
Right, yeah.
This distance is 10 nanometers. This
Okay.
distance is 10 nanometers. This is above, in this case, if you can see here this 990 is down. Here, whatever we have taken, it is down. Here, whatever we have taken, it is up. Why? Because this point is here away from 0, and this point is towards 0.
Oh, right,
Got
right.
my point?
Yes, yes.
Again, any
Sir,
doubt?
Sir,
Yes.
in mesh dimensions, the rectangle, can you move to that where? Yes, sir. In this, what is this 0.040? Actually, 0.020 and 0.040.
0.20 is the rectangle. The width of our rectangle is starting from 0 and it is going to 20. You got that point?
Yes, yes.
And our device is 20 nanometers. That is from 0 to 20.
Okay.
So I want to make a rectangle such that it should be greater than my device. So if I make it anything greater than 20, it will do. If I make it 21 also, it will do. If I make it 22, it should be greater than my device. For safety side, I make it 40. Similarly,
But
here
it
starting
should be
point
40
is 0.
at the both the side, right?
No, 40, it should be 0. It should be greater than, if you can see here.
You're drawing a box.
I don't have pen copy. I told you. This point is, just see y direction. What is this point? 0.
Minus 1 point.
No, in y direction. In the x direction, it is 1.5. In the y direction, it is
0.
0.
This point is 20 nanometers. So where, if this point is 20, where is 40? Here?
Yes.
So the rectangle which I'll make, I'll start from here. Got my point?
Then minus 1.5 by
again, first
40,
of all,
right?
Minus 40 means if it is 0, where is minus 40 with respect to y?
Downward.
Downward. So any point, if it is 0, I can take minus 1 also. So instead of minus 40, I can take minus 1 also. So the rectangle will be like this. If it is 21, the rectangle will be like this. If it is 22, rectangle. If it is 100, rectangle is like this. So it should be greater than our device. Whatever the size of device is there, it should be greater. No matter how big you can be, but it should be greater than our device.
Then on x-axis, it is equivalent to the length of the device.
Equivalent.
Right?
That means it should not be less. It should be greater or it should be equivalent. Ideally, it should be greater. It should be, instead of minus 1510, it should be minus 1.520. Let us change it here. 520. 520. And here it should be 900. Ideally, it should be greater. Here it is exactly with the device size, but ideally it should be slightly greater than what with compared to our device.
Okay.
Anything else? So what I will provide you for the first experiment, this SCM file will be there. This SCM file will be there. Again, this CMD file will be there in your work TCAT folder. You have to copy this, and this setup file will be there. These 3 files will be there in your TCAT folder. You need to copy this. What I'll do, I'll just change the coordinate of the device. Instead of 500 nanometers, I'll make it 400 nanometers. So you have to just change the coordinates accordingly, and rest of the steps will be same.
Sir, like you created lab 1, we have to create our own file.
You will see the ticket folder. You will have a blank ticket. Once you copy the ticket folder, I'll just show you. So this is my ticket folder because I have created my lab 1. When you will see the ticket folder like this. Control L. Yes, so this ticket folder you will see. So here you can find this setup file is there. pnjunction.cmd file is there, and this is the SCM file. So either you can copy the whole ticket folder because in the due course of experiment you will need all these files, or if you want for first experiment you only need these 3 files. You can copy only these 3 files. Got it? So that's all from my side. I'll just post the first assignment 3-4 days before the second lab. I'll post the first assignment. Okay.
So second class will be after 14 days, na?
It will be on 23rd. 23rd of May.
So before that we need to submit.
The soft deadline will be 23rd. If in any case you are facing some problem, you are not able to, I'll just increase the deadline. So that is not the problem. Okay.
Nanometer change will be there. You told for us, correct?
Yes.
You told
What
us.
you asked?
You were telling na that you have plotted this for means we have to modify according to that changes. What you told.
These 3 files will be there. You just copy this file, and in the SCM file you modify according to the given whatever the question I will float. That will be according to that dimensions. You have to make the change in the SCM file.
Okay.
Sir, this will be the first assignment, right?
This will be the first assignment.
So how many assignments will be there in lab then?
I told you there will be EC3 components. There is total 30 marks. Okay. So 15 marks for the assignments. 3 assignments will be there, 5 marks, 15 marks. One will be the situated learning assignment. That will be of 5 marks, 20. And there will be 2 quizzes. So total 30 marks like this. So I'll just end the meeting here. We'll meet on next 23rd of May. In due course of time, if you face any problem, you can just message me in the MS Teams. I'll just try to reply you through the message.
The assignment will be available